Hi, it's Monday, June 15th, 2020. My name is Noah Seeley, and welcome to my channel. So today I thought we would continue our discussion on deep reinforcement learning and start off by introducing our first paper that we will be going over and reviewing. If reinforcement learning is new to you, or you feel as though some of the topics in this video are still a bit fuzzy, I strongly recommend going to my channel and checking out my two-part reinforcement learning introduction video. They're pretty quick and offer some introduction to the definitions, process, and ideas that are important in reinforcement learning. If you're still feeling stuck with it then, I've included some great resources in the descriptions of those two videos that I advise you to check out. With that being said, if you feel that you're ready with reinforcement learning, let's go look at the paper. So the paper today was written by the researchers shown here from the DeepMind Technologies Lab and is called Playing Atari with Deep Reinforcement Learning. So similar to my intro video, I think I'm going to cover this in two parts just so we can break everything up a bit easier. So without any further delay, let's jump into part one of this paper, which will cover the introduction, background, and related work sections of the paper. The paper starts off by discussing the problem of domain selection in reinforcement learning. They comment on how thus far, models have had to take their handmade inputs as feature detection rather than extrapolating their own visual and auditory data. The paper hypothesized domain selection to be replaced by other newfound research in machine learning, such as models that are able to pick up on visual and auditory data. This includes convolutional neural networks, which we've previously discussed on this channel. With that being said, they comment on challenges the transition of these deep learning techniques to the realm of reinforcement learning could be. For starters, deep networks, such as we've seen with convolutional neural networks, require supervised learning from very large training, validation, and testing sets in order to perform as well as they do. The researchers posed the question of how to simulate that type of classification within reinforcement learning, which is a vastly different type of learning compared to supervised or even unsupervised learning. Deep learning also assumes a fixed data distribution, whereas it will vary in reinforcement learning processes through epochs as the agent learns new behaviors. The introduction ends saying that the project was able to implement a convolutional neural network that can control policies from raw pixel data. They used a variant of Q-learning with stochastic gradient descent for weight updates. They also implemented some techniques to smooth out data distributions during training. Overall, they'll use their agent to try and beat a variety of challenges in Atari games that would be difficult even to humans. The overall goal was to use a single neural network agent that could learn as many games as possible without being given any specific handmade references of any kind to any of the games, except simply what a human new to the game would get: video input, a list of possible actions, and signals to indicate success or failure within each game. As we delve more into the paper, of course we'll see more specifically how they did this, but in the end they were able to use an agent with constant hyperparameters and constraints across all games to find success in 6 of 7 of the Atari games they played it on. So the background section roughly describes some very high-level intuition about the reinforcement learning model that will be deployed on the environment, in this case the Atari games. The agent will input an action from a set of possible actions into the environment. The environment will not respond with a reward, but simply change its visual stimulus according to that action, similar to how a game would change as a human plays it. The agent will have to learn actions from the visual cue, as well as the game score itself, which is the other thing it will be in the know about. They mention that the theory of learning here will not be action by action, but instead with prior actions in mind, creating sequences of plays that form strategies to win the game, or at least optimize the game score. The paper discusses how this leads to the formation of a long but finite Markov decision process. They comment that the goal of the agent is to optimize the game score, thus they make an optimal Q function, which will be found when the action that minimizes the score is taken after a sequence or strategy is observed. They also use diminishing returns over time for future rewards, and assume that the game will terminate following this theory of sequences and actions. They say that this function obeys the Bellman equation, which essentially says that if the optimal sequence in a given state was known for all actions, the agent will always choose that optimal action. Thus they show that by using the Bellman equation, finding the optimal solution is possible through iteratively updating the action value function until it converges to an optimal solution. The agent will use an action value estimation because apparently it's impractical to be able to find an optimal solution through the described method. This estimator is usually a linear function, but here, as mentioned, they use a neural network. The neural network is known as a Q network, and it will basically train in the typical fashion by updating its weights in order to minimize a loss function. This section goes a bit more into the math behind those updates, but the important takeaway is that during the weight update for the Q network to learn, the target values are taken from the previous score of the action state function. This shows how the learning contrasts that of supervised learning, where the targets are always fixed endpoints. This section finishes by saying that the agent is model-free, as they are directly using samples from the environment. It is also off policy, as it uses a greedy strategy of taking the highest score that comes out of the state action function, while following a behavior distribution to determine its actions. I'll quickly finish this part with discussing the related work section, and it starts off by saying that at the time, there wasn't much prior work done related to the work suggested in this paper. They say the only non-linear neural network using reinforcement learning they could find was a model that could play backgammon really well. Though it found success in one game, it couldn't generalize to find that success in others, which contrasted the research done here, as they want to find an agent general enough to learn a variety of games. They comment that the difference between a lot of other work and this paper is that the agent will take visual directly from a convolutional neural network and shoot it right into a reinforcement learning algorithm, rather than having any pre-processing of that visual input from the game. They quote that they believe this may help the agent learn features that are relevant to discriminating action values. The section concludes by describing some previous work in the field that also used Atari games. So yeah, that concludes my part 1 of the discussion on the Playing Atari with Deep Reinforcement Learning paper by the DeepMind Technologies team. I plan on posting a video of part 2 that goes over the rest of the sections in the paper soon. There are also some more technical bits in the sections today that I did not delve into as much, so as always, I've linked all resources that I've used in the description below for you guys to go check out yourselves. If you feel I've missed anything or got anything wrong, please let me know in the comment section below. That's all for today. Thanks for watching. See you tomorrow.